Hello students, happy morning. Class 12 Physics, Unit 6 Ray Optics continuation video. In our previous class, we discussed about the angle of deviation for a prism. Therefore, we used a monochromatic light. Monochromatic light means single color light. Here in today's class, let me see one of the phenomenon of light, that is dispersion. Dispersion. Okay. Here, this dispersion can be done by with the help of the prism. Okay, dispersion means splitting of white light into its constant color, that is known as dispersion. Okay, if suppose I consider a prism, okay, these two are the refracting surface, this is a rough surface. Suppose a white light is made to fall on a prism. Okay, after refraction, okay, it is a extended incident ray. After refraction, it will bend its path. Okay, here the white light, it bend its path, we get a spectrum of light. Okay, it will start from red to violet, that is VIBGR. Okay, this band of light is known as spectrum of light. Okay, from this observation we found that the violet, it is the most deviated color. Violet is the most deviated color, and the red is the least deviated color. Okay, see, dispersion, that means a white light is made to fall on a prism, it split the white light into its 7 constant color, that is known as dispersion. Okay, here this is known as spectrum. Okay, the band of color of light is known as spectrum. Here from that observation I found that violet is the most deviated color and red is the least deviated color. Okay, here the color obtained in the spectrum, that depends on the nature of the light source. Okay, this is a light source. Okay, then we found that each color in vacuum have the definite wavelength. Okay, each color in vacuum have the definite. Violet have particular wavelength, indigo have particular wavelength, and red have the particular wavelength. See, here red have the wavelength, red have the largest wavelength, that is lambda is equal to 700 nanometer, and the violet have the least wavelength. Okay, that means shorter wavelength, that is lambda is equal to 400 nanometer. Here nano, n is equal to, that is nano means 10 power minus 9. Okay, then these all the colors are different wavelength. Okay, all the colors have different wavelength, they travel with the same speed in vacuum. They have different wavelength, but they travel with the same speed in vacuum. Okay, at the speed c is equal to 3 into 10 power of 8 meter per second in vacuum. In vacuum, all the colors, violet, indigo, blue, green, yellow, orange, red, all travel with the same speed, that is 3 into 10 power of 8 meter per second. From that we found that velocity of light in vacuum, that is independent of wavelength, lambda. Okay, so we can say vacuum is a non-dispersive medium. That means it can't disperse the light. There is no dispersion occur in vacuum. Non-dispersive medium. Okay, but in a medium, see, but in a medium, red travel with a high speed comparing with the violet. Okay, but in medium, red travel with a greater speed. But violet travel with the least speed. This is because, see, we know the expression that connecting wavelength, frequency and velocity. Velocity of light in vacuum c is equal to nu into lambda. Okay, here lambda is a wavelength and nu is a frequency. We have to know one important thing. Frequency of the light in any medium will be a constant one. Frequency is constant for all medium. Okay, then the velocity of the light that depends on wavelength. Okay, here this is a condition for velocity of light with wavelength in vacuum. But for in medium, this is represented as V is proportional to lambda. Okay, for medium we can consider the velocity of light as V, but for vacuum we must consider that as C. Okay, in medium V is proportional to lambda. If wavelength increases, then the velocity of light increases. Due to this reason, red travel with a greater speed and violet travel with a least speed, because the wavelength of the red is greater than the violet. Okay, here the dispersion take place due to two reasons. Okay, let me see. The dispersion take place due to two reasons. First one is dispersion take place in a medium, that is because of difference in speed of different color. Medium. Okay, that is because of difference in speed of the different color in medium. And the second thing is refractive index of the material different for different medium. Refractive index of the material is different for different color. Okay, due to these reasons, dispersion occur in a medium. Okay, here I consider for violet. Okay, for a violet color, refractive index, that is NV, is higher. Okay, then for the red light, that is red color, refractive index of the red, that is least. Okay, here let me see what is dispersive power. Okay, dispersive power, that is nothing but it is a ability. Okay, dispersive power is a ability of the material to produce dispersion. Dispersive power means ability of the material to produce dispersion. Dispersive power is a ability of the material to produce dispersion. Okay, here first of all I consider a prism, then a ray of white light that fall on the prism. Okay, it is a extended instant ray. There will be refraction take place like that. Okay, here it is a red, it is a violet. Then the angle between the instant ray and the deviated light ray is known as angle of deviation. It is a deviated angle for red light, so it is considered as delta R. Okay, then here it is a deviated angle for violet, then delta V. In our previous class we found that the angle of deviation is represented by the symbol small d. Here we are considered as delta. Okay, see, this white light is made to fall on a prism. It will disperse that white light into its constituent color. Okay, here there are large number of colors in between the violet and red. Okay, here I am considering the violet and red alone. Here I consider the prism. This prism is a small angled prism. Okay, it is a small angled prism. For a small angled prism, the angle of the prism will be in order of 10 degree. Okay, in order of 10 degree. For that, the angle of deviation also small. Angle of deviation also small. So we can consider D as delta. Okay, then we know here we found that the refractive index of the metal of the prism is n is equal to sin a plus d by 2 by sin a by 2. Okay, I am solving this as sin a plus delta by 2 by sin a by 2. Okay, here the angle a and delta are very small. Okay, so we can consider sin a plus d by 2 is approximately equal to a plus d by 2. Okay, then sin a by 2, sin a by 2 is equal to approximately equal to a by 2. Okay, then the refractive index became n is equal to a plus d by 2 by a by 2. That is here it is not d, that is delta. Okay, delta delta. So we can write a plus delta by 2 by a by 2. Here 2 going to cancel, then we get n is equal to a plus delta by a. Okay, we get n is equal to a plus delta by a. On solving this, n is equal to 1 plus delta by a. Okay, and again I solved it, then n became or take this 1 as this side, then n minus 1 is equal to delta by a. We need delta alone, so we can write delta is equal to n minus 1 into a. Okay, this delta is nothing but the angle of minimum deviation. Okay, this delta is an angle of minimum deviation. Here the delta that depends on the refractive index of the material of the prism and the angle of the prism. Okay, see, when a white light enter the prism, the deviation is different for different colors. See, if a white light enter the prism, the deviation is different for different color. Okay, red is least deviated and violet is more deviated. Okay, so we can consider delta V and delta R, that are angle of minimum deviation for violet and red. Angle of minimum deviation for violet and red. Okay, and NV and NR, that is refractive index of the color violet and red. Index of color violet and red. Then I am writing the angle of minimum deviation for violet and red. Okay, for violet. For violet, angle of minimum deviation del V is equal to NV minus 1 into A. For red, angle of minimum deviation of red color is equal to NR minus 1 into A. Comparing this, we know very well angle of deviation of violet is greater than angle of deviation of red, and the refractive index of violet is greater than refractive index of red. Okay, here I consider this one as equation 1, this one as equation 2, here 1 minus 2. Okay, then we get del V minus del R, that is equal to NV minus 1 A minus of NR minus 1 into A. Okay, on solving this, then we get 1 going to cancel, then NV minus NR R, sorry, that is A. Okay, then del V minus del R. Here del V minus del R, that is nothing but the angular separation. Angular separation. Here it is an angular separation between the two extreme colors. The extreme colors are violet and red. Okay, the extreme colors are violet and red. Angular separation is a angular separation. Okay, the del v minus del r is a angular separation. Here angular separation between the two extreme colors that are violet and red, that is known as angular dispersion. Okay, here this is known as angular dispersion. See, the angular separation between the two extreme colors, that is violet and red. Okay, two extreme colors in a spectrum is called angular dispersion. That is del v minus del r, that is a angular dispersion. Okay, here we can see in between the red and violet there is a large number of colors, that is it is represented violet, indigo, blue, green, yellow, orange, red. Okay, the middle color will be a two color, that is vibgyor. Okay, vygyor. The middle color is blue, green, yellow. These are the middle colors. Okay, the middle color will be green. Okay, for that green we can write the angle of minimum deviation. For that color we consider that one as delta. Okay, for the middle color, the angle of minimum deviation, that is delta. Okay, then the refractive index of that color I consider that one as n. Refractive index, that is n. So we can write delta is equal to n minus 1 into a. Okay, delta is equal to n minus 1 into a. Then let me see what is dispersive power. We know dispersive power, it is the ability of the material to produce dispersion. We know del v minus del r, that is the angular separation, and del is equal to n minus 1 a is the angle of minimum deviation for the middle color. Okay, it is the average one. Then let me see what is dispersive power. Here we know very well dispersive power is the ability of the material to produce dispersion. Okay, we can write dispersive power in terms of angular separation and middle deviation. Okay, using these two expressions we can write dispersive power. Dispersive power is represented by the symbol omega. Okay, dispersive power, it is a ratio of angular dispersion to the middle deviation. Okay, we know angular dispersion, that is del v minus del r by middle, that is middle deviation is del. Okay, that is delta. Then we can write omega is equal to delta v minus delta r by delta. Okay, here delta v minus delta r is nv minus nr into a by n minus 1 into a. Here a going to cancel, then omega is equal to nv minus nr by n minus 1. Here the dispersive power, okay, it is a dimensionless quantity. Here it depends on nature of the material of that prism. Okay, here dispersive power is a dimensionless one, dimensionless quantity. Okay, and it depends only on the nature of the material on which the prism is made. Okay, dispersive power is a power of ability of the material to produce dispersion. Okay, dispersive power of vacuum will be 0 because there is no dispersion occur at a vacuum. Why dispersion occur in medium? Because of change in speed of the different colored wavelength and also change in refractive index of the different color in the material. Okay,